So this lecture will be more theoretical, but is useful with the aim of modeling the response. We have the response of fiber reinforced materials to loading. So in order to model the response, which can be done also by some of you. Yes. You need a model, mechanical model. And so this is a model that I have developed over recent years in collaboration with colleagues in the United States and Europe. And so it's a particular model for fracture. It's not a standard model for modeling crack propagation in materials and crack initiation and propagation in materials. And so it's something that can be useful for research purposes for the reason that I will describe. And so it can be used, for example, to model the interface or the response of the material in through finite element methods, for those of you who can be interested. So the idea is to okay, let me restart. There are other people. So I was just mentioning the goal of this presentation, which will conclude the theoretical part of this today session, because the final part will be about the 3D printing, and we have other fibers. Elenia, we have other fibers to print. No, we do later. We do later. But we have other, we have the cylinder, we have the fabric. The cylinder and the fabric. So we can experiment other fibers, to 3D printing of other fibers. This lecture is more, is on the theoretical side, and wants to describe a mechanical model to reproduce the crack propagation phenomenon in materials that are fiber reinforced, typically. So the goal is to use all energy, just an energy approach to fracture propagation. So to model the fracture propagation through energy minimization, without criteria, without any other criteria. For those of you who work in fracture mechanics, who have been involved part-time in fracture mechanics, it is known that if you want to predict the propagation of an existing crack in a body, you have to usually employ a criterion. You assume that the crack propagates in the direction of the maximum tensile strength, or in the direction of the minimum of the maximum deviatoric component of the stress. There are a few criteria. We want to avoid any criteria, and we want to model the fracture through pure energy minimization. So this is the goal of this model. It falls in the category of free discontinuity problems, because the discontinuity in fracture is basically the fracture itself is a discontinuity in the material. And the free discontinuity problems are the problems in which the the set of the discontinuities, which is the crack pattern in our case, is not known in advance. So the crack pattern is not known. So the discontinuity set, the discontinuity set of our problem is not available, is not known in advance. So the problems which treat the problems dealing with discontinuities that are not known in advance are called free discontinuity problems. Our problem, our fracture problem is described as a free discontinuity problem. And yes, I have this. And we propose a particular approach to free discontinuity problems, which I will describe in detail later. So let's assume, first describe what is a free discontinuity problem. You search for the minimum of a given energy, which is function of two variables. Usually the energy in most cases is a function of the displacement, okay, or the deformation map, assuming phi might be the displacement or the deformation map, depending on small displacement, large displacement, so on. Usually the energy that you want to minimize is a function of the displacement field. In free discontinuity problems, the energy is a function also of the discontinuity set, because the displacement allows for discontinuities, which are basically the opening, due to the opening of cracks. And so the energy is a two-field, depends on two fields. The deformation mapping, phi, or the displacement phi u, and k. K is the crack pattern in our case. It's the set of the discontinuities of phi, of the deformation mapping or the displacement field. And so this energy is done by an elastic part. These other two parts are not very important. The elastic parts, assuming elastic fracture to occur, the first term is the bulk term, is called the elastic energy. Is the integral of an elastic energy density, which is basically the energy due to the elastic deformation of the body. So this is a volume term. That is which is the support of this energy? Is the body. Omega is the body. Without the cracks, is the part of the body where cracks do not occur. In this part, the body is elastic, assuming. Can be also plastic, but let's treat elastic fracture first in this presentation. So this is the elastic energy over the uncracked portion of the body. Those other two terms are boundary terms, which are this is the contribution of body forces, if body forces are applied, and this is the contribution of surface tractions to the energy. Okay, those are body forces and surface forces terms to the energy of the energy, and this is finally instead this is what needs to be added. Different from standard problem, there is an interface energy. This is defined over the crack pattern. So it's the energy that is released due to the opening of cracks. So this energy, let's forget about those two parts, which are, you can basically neglect those two terms if you are applying a displacement loading, assuming that you grip your specimen in a testing machine and you apply a displacement loading, you won't have body forces and you won't have surface tractions because you are applying displacement and not forces. So assuming displacement controlled loading, those two terms are missing, and only the first and the last term survive. The last term is the integral over a surface now, because k, while omega is a volume, in the case of a 3D body, or an area. If you are talking about a 3D body, omega is a volume, and k is a surface, the cracking surface. If we are thinking of a 2D problem, omega is an area, and k is a line. Okay? So this is the bulk term, the volume or area term, and this is the surface or line term, depends if we are in 2D or 3D. So this energy is this term is related to energy density. The energy density is referred to the unit per unit surface of the crack, or per unit length of the crack, if we are in a 2D problem. So this is the energy density per unit volume, the elastic energy density. This is the fracture energy density per unit surface. So we are minimizing an energy which is composed, let's drop these two terms for simplicity. There is a bulk term and a surface term, if we are in 3D. And those two terms compete each other. And we want to minimize this energy, so the fracture occurs. When does fracture occurs? When, by cracking, if you open a crack in a material, if we ideally crack this, because I need it, this mouse, what happens is that the fracture energy increases because we are opening a crack. So we need to spend some energy to increase, to crack the body. We are spending some fracture energy, but we are gaining some elastic energy, because what happens if we crack this, suddenly the form, it releases some elastic energy. So when those two terms balance, fracture occurs when, assuming there is a given energy, this body has a given energy, initial energy. Then we ideally open a crack, we spend some energy to open the crack, we gain some energy due to the reduction of the stiffness of the body, because the body becomes more compliant, we gain some elastic energy. If this balance is the energy that we gain, the reduction in the elastic energy equals the crack energy that we need to provide, the surface energy that we need to provide to open the crack, when this balance occurs, the crack opens. When the energy that you spend to open the crack is greater than the energy that you gain due to the reduction of the compliance of the body, the crack does not open. When the release in the elastic energy is greater than the fracture energy that you have to provide, the crack propagation is unstable. So you can describe the fracture response through this energy. It's composed of two terms, basically, one bulk term in the uncracked region and one surface term in the cracked region. And the competition between these two terms will decide whether the crack propagates or not, and in which direction also the crack propagates. Because this test that I have described I have assumed to open a crack in this direction. Okay? I make a balance. But you can imagine to ideally imagine cracks in all the possible directions. You have to make this balance for all the possible cracks. There is no unique crack pattern that you can imagine. So there are several crack patterns that you can imaging, and you have to test this balance, this energy balance, for all the possible crack patterns. So the crack pattern is a variable of the problem. Okay? And if we are able to make this balance for all the possible crack patterns, we will obtain the response to the first problem, the crack propagates or not. The second problem, along which direction it propagates. It propagates along the direction in correspondence of which this balance occurs. So the decrease in elastic energy equals the increase, the energy, the surface energy that must be provided to open the crack. And so this is the idea. I don't know. I cracked the pointer and it doesn't work anymore. It works as a pointer but not as a... Okay. Unfortunately, this... No, nothing happens anymore now. Let me see if I have any chance. No. I got stuck again. I don't know. It works again. So, what is the shape of the surface energy? There are several kinds of fracture. The surface energy is the energy that you have to provide to open the crack. It can be a constant, the typical of the material. And that is the case of a purely brittle material. So the energy that you have to provide to open a crack does not depend on how much you separate the crack lips. It's a constant. So to open a crack, if the material is brittle, the energy that you have to provide, it does not depend on how much you open the crack. It's not a function of the crack opening displacement. It's a constant. And this is the case of purely brittle material, like concrete without reinforcements, and like glass, for example. Then you can have other models in which, on the contrary, the energy density depends on the crack opening displacement. Delta is the crack opening displacement, or the effective crack opening displacement. If you have mode 1 and mode 2, so you open the crack both normally and tangentially to the crack surface. If this function can have different shapes, you can have the different fracture model, which is called cohesive fracture. In cohesive fracture, the surface energy density depends on the crack opening displacement. Because in the cohesive fracture, you can imagine that there are some bonds. When you open a crack, there are still some bonds between the crack lips that continues to be active. So you have to provide additional energy to open, depending on the energy that you have to provide depends on is a function of the crack opening, until you get to the plateau in which basically you break the bonds, and so you go back to the brittle case in which you have the energy does not depend anymore from the crack opening displacement. Up to a given displacement, it depends on the crack openings. Then it becomes a constant because you have broken the bonds. This is the cohesive fracture. Usually ductile material obeys to the cohesive fracture, and brittle material obeys to Griffith model. The material toughness is basically what we have measured before. Is this quantity. The energy, the toughness of a material is the energy required to open a crack in that material. Okay? Refers to the brittle model. So our model, which we name eigenfracture, is complicated mathematically, but the mathematical proof is a bit complicated. All the mathematics is behind this model, but the use is pretty simple. Very simple. It can be used without writing a finite element code specific to this model. You can use a standard finite element model and to predict crack by spending some time with the standard code, but you don't need to write a finite element code. So your energy is made of two terms. Okay? Our energy is made of two terms. This is the elastic energy, and this is, if you have a brittle fracture, assuming brittle fracture, what is the fracture energy? It's the toughness of the material, the energy per unit surface of the material, times the area of the crack. No? Because if we are in this case, so the crack energy does not depend on the opening. So the energy that you release is just a multiplication of the property of the material, which is the toughness, the fracture toughness, times the area of the crack. Okay? So in our model, we introduce a damage variable. Okay? A damage variable, which is a measure of the strain that occurs in the cracked region. So we regularize the problem by, instead of introducing discontinuities, we introduce damaged regions which approximate the discontinuities, the fracture pattern. So there is this gamma, we introduce a gamma variable. The elastic energy is function of the displacement gradient, EU, or the elastic strain, EU, minus this damage variable, and we measure the elastic energy, the fracture energy as G. G is the toughness of the material. We call it G as is standard in the literature about fracture mechanics, times what we should multiply G times the measure of the cracked region, okay? The dimension of the damaged region, in order to approximate the fracture, the energy formulation of the fracture problem through a damage variable. We should have G times the region where gamma is different from 0. The measure, the volume, or not the volume, in this case is a volume, because we are reproducing fracture, we are reproducing the fracture, we are approximating the fracture as a damage. So this gamma is not a discontinuity of displacement, it's a damage. It's like a strain, it's like a plastic strain. It's an eigen deformation, that's why eigenfracture, the name of the model. So you have this damage variable, so we are coming back to a continuous problem in which we approximate the crack discontinuity through a damage variable. You can think this way. There is the undamaged region of the body in which gamma is 0. Okay? And there is the damaged portion of the body in which gamma is the total strain. The total strain, all the strain is gamma. In the damaged region, you won't have elastic energy. Why? Because the energy minus, the strain minus gamma gives 0. Okay? So this is the elastic strain. So the strain minus gamma is the elastic strain, and the fracture energy is taken as G over 2 epsilon, the measure of the region in which gamma is different from 0. So this is reasonable. We have to understand what is this epsilon here. Okay, but this is reasonable. So we take the energy as a function of two variables: the displacement field, the strain, the displacement field, which gives the strain, and the damage variable. We don't have K. We don't have K anymore as variable. Our variables are still two, but are not U and K or phi and K. Are U and gamma. Okay? Gamma can be in each element, but in the end, we want that this gamma is equal to the strain in the cracked elements and 0 in the damaged elements. Okay? But we don't know where this gamma is. We don't know where the gamma is. And the energy that we want to minimize, we want to know where gamma is, which elements are damaged, by minimizing this energy. So the minimization of this energy should tell us which elements are damaged or which not. Okay? If we put a gamma in a, we say this element is damaged, the energy decreases? Yes. Okay. That is a good candidate to fracture. Then the body gets damaged or fractured, and you can continue trying to damage elements. You will try in the end with a finite element code. You know what to do. You remove elements. You remove one element because in our model, gamma kills the element. If we damage an element, it's like removing that element from the finite element model. If it is cracked, it doesn't exist. We remove it. But we have to try removing the elements and seeing if the energy decreases. So we can kill any element, and we will kill the element only if the energy decreases. So the energy before killing the element and the energy after killing the element, because you will obtain without the element. Imagine that you have a body subject to a tension test. You have a displacement field and you have an energy. Now you kill one element. The body will have a different strain field, will have a different elastic energy, and you will have added a fracture energy needed to kill that element. And if the increase of so the fracture energy that you have to provide to kill that element is balanced by the reduction of the elastic energy, that element can be actually killed. Otherwise, it won't be killed. Okay? But how do you measure the energy of that you need to kill the element? That's the trick. That's the trick that you have to learn, because otherwise this doesn't work. Because engineers have tried for many years to do this. What do you do if you want to model a crack? You remove some elements. This has been tried many times. It's not our invention. It's an old story. But it doesn't work if you don't do it properly. So how you measure the energy that you need to crack an element? Okay, so gamma different to 0, the measure of gamma different to 0 would be the volume of that element. Okay? One can think, okay, I take the volume of the element that I want to kill, and I multiply to some constant, and that's the volume that I need, that's the energy that I need to spend. First, remember that the energy to create a crack is energy per unit surface, while we are killing a volume. We have to normalize the volume. We have to normalize the volume to a length in order to obtain a surface. So this is the rule of this epsilon. I will show you through a picture. Assume that you have a crack. You want to approximate this crack. And you want to approximate by killing those elements. Why? Because you have a finite element mesh. It doesn't know the element mesh that you are using. It doesn't know where the crack is. It's a standard. So you won't have elements placed along this line, no? Okay? You will have elements that will be close to this line, and you want to kill those elements to replicate a crack propagating along this line. Which energy you spend in this way? If you can think, okay, epsilon is if H is the size of the element, the size of the element is of a finite element method. A finite element is basically the major dimension of the element. Because the major distance between the points of an element, if it is a triangle, is the major side, the side of major line. That is H. H is the size of the finite element, which is the maximum dimension of this element. One can think, I take the volume, the red volume. I divide by this H, and which gives a surface. In this case, if you are into D, this is an area. The red is an area. We divide by H, which is a length. We obtain a length. Okay, an area divided by a length, you obtain a length. And we multiply this gamma over H times the surface energy of the body, the fracture toughness. And this is the energy that we imagine to spend to kill those elements. If we do this, the procedure will fail, will not be able to, will not work, will be mesh dependent. Because the problem with this kind of trick, cancelling elements, is that the trick is mesh dependent. Because it depends on the mesh that you have used. If you use a different orientation of the mesh, you will add a different crack. So it's mesh dependent. And how you understand that? If you take the measure, if you do this, the area divided by H, this measure of this set will be greater than this because of zigzag. So the measure of the center line of this is not equal to the inclined line. It's not equal. So you are basically not, you get a prediction that is mesh dependent, that does not, you can take the mesh size as small as you want. There will be always a difference between the length of this zigzag line and the straight line. So this approach will not converge when you use very, very fine elements. The trick is this one. You don't take that measure, you don't calculate the energy spent to kill those elements in this standard way. You compute in this other way. You don't take the set where gamma is different by 0, but you take the set in which of the elements which are at a given distance epsilon from the sets where from the damaged sets. We take all the elements which are at a given distance epsilon is a parameter, from the crack set. So the blue region is the set of the elements, is what we call the epsilon neighborhood of the damaged region. Let's consider the epsilon neighborhood of the crack region. What is the epsilon neighborhood? Is the set of all the elements that are at a given distance epsilon from the damaged region. Okay, it's the blue area. Take that blue area. Divide over 2 epsilon. This is epsilon, this is epsilon. Take this area, divided by 2 epsilon. This gives you exactly the length of the center, the straight line. If you take the epsilon neighborhood of the crack and divide by 2 epsilon, you compute the energy necessary to kill those elements correctly. So this is a simple test. You take an element, but you want to kill this element. You want to kill an extra element here to see if the crack propagates or not. You have to compute the energy this way. You remove that element. When you remove that element, you obtain a new solution from the finite element code and a new elastic energy. Okay? You remove the element. You set the elastic moduli to 0. This is simple. To remove an element, you don't even need to remove it. You have the material properties of that element, 0. And you recompute the solution through the finite element code. You will get a different solution from the one with the element in place. And you get a different energy. This was in the integral I think it's a standard quantity computed by all the finite element codes. And then what do? You have to compare this new energy with the energy that you have spent to kill that element. Otherwise, it's always decreasing. Okay? You have to compare. You have to measure what is the quantity to compare. Since you do this by hands, you kill the element. The software gives you the new energy. Usually, the standard commercial software gives you the energy associated with a given solution. Okay? You have to compare this energy with what? With the energy that you have spent to kill that element. And how you compute the energy? You take that element, you take the epsilon neighborhood of that element, so you measure all the elements that are at given distance epsilon from that element. You multiply this volume or area, not the volume of the element, but the volume of all the elements that are at the given distance epsilon by that element. You take this volume, which is the epsilon neighborhood of the killed element, okay? Is the set of all elements that are at distance epsilon from the elements that you are killed. This is the epsilon neighborhood. You take that volume or area, divided by 2 epsilon, and multiply by the fracture toughness. And this is the energy that you have spent to kill that element. Okay? Obviously, when you kill the elements in the epsilon neighborhood, you have to remove the elements that have already been killed before. So you take the killed elements, and you take all the elements that are in an epsilon neighborhood of that element. You obtain a volume or a surface, depending if you are in 3D or 2D, divide by 2 epsilon. Epsilon is a parameter. It's a parameter. And you divide this volume or area by 2 epsilon, multiply for the fracture toughness, that is a property of the material, and you obtain the energy that you have spent to kill that element. If the energy that comes from the finite element solution due to the cancellation of that element is this reduction of the elastic energy as compared to the energy without the killed element is greater than the energy that you spend to kill the element needs to be killed. Otherwise, you don't kill the element. And you try and you try. Okay? So, without going into the details, I will show you the examples. In some examples, the full rank model is the one that I want to show you, is the one with there is also another version of this model in which you don't kill the element, you weaken the element. But let's forget, the easy implementation is of this model is killing elements. You kill the elements, okay? But you have to compute the price correctly, the price that you spend to kill that element, okay? And there is this epsilon neighborhood technique. If you don't do the epsilon neighborhood technique, your result will depend on the mesh that you have used. The epsilon neighborhood is an average. It can be seen in many ways, complicated ways mathematically. Is a kind of convolution technique or averaging technique in order to correct the mesh anisotropy that otherwise you will get with your prediction. So this is in the case of a beam with an original pre-crack. This is pretty easy. Where do you search the cracked element in this case? Near the initial, in this region here, no? You try to crack this element, and you see if it is convenient or not. So if the total energy decreases or not. So when do you crack really an element? When the total energy, which is the summation of the elastic energy and minus the fracture energy, decreases, okay? Or plus fracture energy decreases, plus. So, oh, the movie doesn't start. New movie here. Oh, okay, starts. Did you see anything? No? I'm asking too much to the... we can see the movie from outside the presentation. Oh, he doesn't like it. But if I open it with the oh, that's too bad. Okay, this is, we're not able to show the movie, but if you do this, by standard examples in which you have a plate with an initial crack and you apply displacement according to given directions in mode 1 is orthogonal to the crack, or you have more mixed mode by applying displacement that are inclined to the crack. If you do this, you can repeat this test. This is what we got. So this is the solution that we got. These were the elements that were convenient to crack in order to reduce the total energy. And this is the prediction of the crack. But you have the price, it is simple. You crack the element, you have to learn this epsilon neighborhood technique, which is pretty easy in the end. What is epsilon neighborhood? You want to kill this element. Let's remember, you try to kill this element. What do? You set this element, all the elastic moduli of that element to go to 0. Okay? And you obtain a different energy. Okay? And you compute the delta energy, the difference in the energy without killing the element and then killing the element. You have a difference in energy. You sum to this difference in energy the energy that you spend to kill that element, that is computed by computing the epsilon neighborhood of the element that has been killed. So the area, in this case, of all elements that are at distance epsilon from the center of the element that you want to kill, where epsilon is a parameter. Okay? Then you divide this by 2 epsilon and you multiply by h, and you compare this increase of the energy with the decrease of energy due to the cancellation of the element. If this balance is positive or equal to 0, you cancel that element. Okay? Otherwise, you don't cancel. And you have just to try. Obviously, in most cases, you know where the crack occurs. Otherwise, it's time consuming. You have to let the computer do all this. You cancel this. You have like a matrix. I cancel this. You have to do this in an iterative way. You have to teach a computer to do this. In simple cases, you do manually. Otherwise, you have to teach a computer to do this. But you have a way, a simple way, to predict crack propagation. And we compare this to literature results, and we were able to theoretical and the literature results, we were able to confirm that the approach works. What is epsilon? Epsilon has to be, how do you choose epsilon? Epsilon has to be 3-4 times the mesh size, because you have to build the epsilon neighborhood. Epsilon cannot be smaller than h. Okay? H is your mesh size. The mesh size depends on the computer you have. It's the size of the elements, the largest size of the element in the process zone. You take epsilon 3, 4, 5 times this h, and then you have and you use epsilon in the form that I described. Obviously, this works theoretically. It has been proven that it works when epsilon goes to 0. It means that you have to have very, very fine meshes, and if you use very, very fine meshes, at least in the process zone, you will predict the real crack. And we obtained confirmation of these results, and we also did the pull-out test that could be of interest for. So in this case, if you want to use this method to predict the pull-out strength, pull-out is not exactly the proper word, because this is normal to the fiber. But which are the elements that you would like to try to crack? Those ones. Start with this, then that, and that's what you obtain by letting the displacement to increase. And so this is a tool to predict. For example, we wanted to see to predict the toughness of a fractal fiber. You can use this, but you need a very fine mesh, because the mesh sides will be linked to the sides of the fractal geometry, and then you need to it should be the mesh sides should be lower than the sides of the fractal shape, and then these sides must go to 0 in order to get to predict the real crack formation and in the material. But in our case, maybe we just want to predict when the first element cracks. If we want to predict the post-cracking behavior, we have to predict also the propagation of the crack. But if we are interested only in the first crack strength, we have to we can investigate on the value of the occurrence of the first element killing according to this energy balance. Okay? Now, in the final part, I hope this was not too heavy. I tried, but in the end, the use is easy, but the theory behind is a bit more, it's a bit complicated. And now, I don't know if I cannot use anything anymore, but this is because of the table. Okay, let's do this. Narinder, can you please help me? I don't see the cursor. Where the cursor is?